Now, to prove the cosine rule, we drop a perpendicular in the triangle. Now, I have labelled this triangle in such a way that I will end up deriving this form of the cosine rule. You don't have to be memorizing what way to label the triangle. If you happen to have labelled it differently, maybe you call this side over here A and this one B and this one C, you'll end up getting, say, B squared equals A squared plus C squared minus 2AC cos B. This is fine, as long as these are corresponding. So small b is a side, capital B is the corresponding angle. If you have it labelled some other way, you may end up with this version of the cosine rule. Again, this is fine. These are corresponding. And the other sides appear in here. They're squared and added here, and they're multiplied together here. So I explained in the last video that normally I work with this version of the cosine rule. If I'm looking for a side, I call it small a. If I'm looking for an angle, I call it capital A. So it's just less confusing to work with this version. Of course, the other two versions are identical to this. We've just changed around the labeling of the sides and angles. So what I will do here is call the distance from this point to this point x. Now the total distance or length of this side is b. So if x is the distance from here to here, then the distance from here to here must be b minus x. Of course, if we add x onto b minus x, we get b. We are going to look at the two right-angled triangles that are formed. First of all, let's look at cos of A. That's going to come into this version of the cosine rule. Well, if we look at this right-angled triangle here, we can see that the cos of A is the side adjacent to A. Now, the side adjacent to A is b minus x. And the hypotenuse of this right-angled triangle is this side here, small c. Now, let's get the perpendicular height h in terms of the sides of this right-angled triangle. We don't want h to appear in the cosine rule, so we have to eliminate it some way. So let's first of all look at this right-angled triangle. We know from Pythagoras' theorem that the three sides are connected. We know that the square of the hypotenuse is c, is the sum of the squares of the other two sides. So the other two sides are h and b minus x. And we can rearrange this to get h. Remember, we don't want h to appear in the cosine rule. So h squared is equal to b squared minus b minus x squared. We can look at this other right angled triangle and do something similar. We can apply Pythagoras' theorem, and we also get that h squared is the hypotenuse squared minus this other side squared. So we can see that both of these expressions are equal to h squared. They're equal to the same thing, so they must be equal to each other. So we have that a squared minus x squared must equal c squared minus b minus x all squared. So squaring this out, we get b squared minus 2bx, and this minus sign will give plus 2bx. Then we have plus x squared when you square the minus x, and then the minus sign gives us minus x squared. We can see that the minus x squareds cancel out. So you can see now that this thing is shaping up to look like the cosine rule. We have to deal with this x. Well, we get rid of x by considering this here. We rearrange this to make x the subject. So we see that b minus x equals c cos A. And from this we get x equals, if we bring the b across and change signs, we're going to get x equals b minus c cos A. So we plug this in for x. So now we copy down this line here. We have a squared equals c squared minus b squared plus 2b times x, where we plug in b minus c cos a. So now we have a squared equals c squared minus b squared plus 2b squared minus 2bc cos a. And you can see now that we're very nearly there. Just one more line. A squared equals, well, plus 2b squared minus 1b squared is b squared. And then we have plus c squared. And finally we have the cosine rule.